1.5. Standard deviation is 16.7. So at the end of today's lecture, we will return the graded examination sheets, so that you can check together with the solutions. You can check if everything is fine, or you need to make correction with TA. Okay, that's the midterm examination. Ladies and gentlemen, this is only relative, grade, not absolute. I believe all of you have spent a lot of effort learning this subject. As I mentioned, this subject itself is non-trivial. You need to spend a lot of time, and if you do now, you have in-depth learning. I can guarantee it will help you in your future 20, 30 years. Okay, then for the final examination, I will think how to offer examination problems. Sometimes examination problems not trivial to prepare, so that it is more suitable to reflect your learning results. But that's for my experience, for my reference. So I hope that this teaching can help you to enhance or upgrade your knowledge, to build up. This is essential knowledge. I explained those tools are, we say, guided missile. It's very, almost the front end, at the front end of the battlefield. You can use it. Well, okay. Now we come back to section 4.4.2. Last time, just the presentation tools not ready, and we spent a lot of time, but that distracts my teaching. So that because the section 4.4.2 is hard to fully understand. So today I'm going to spend a little bit more time to review all the materials so far in section 4.4.2, the vector optimization. Okay, last time we defined a problem. The generalized inequality happened to be, change another color. Which color? Better. This one. The objective function is a vector or matrix. So you can, if you want to compare F0x, then you need to use a generalized inequality. As I mentioned, generalized inequality is defined by a protocol. So different protocol and different comparison rule. Okay, then for the feasible set, the same as before, ordinary inequality and equality constraints. So the F0 is a vector, a 2x1 vector. So that's for the time being. F0 can also be a matrix. Here, we use Rn or Rq as a vector. That means F0. So we define the set O is the image of F0 C. C is the feasible set. This is a feasible set. So in other words, after you transfer or you convert this problem into a set O, then next step to find out the optimal point, or we say minimum points, or minimal points of the set O. This is the job we want to tell, we want to cover. Then, as you know, for let me use this. Yeah, then I thought you should be able to understand this. Okay, this page is example O is here. We have a O, this set. So we want to find the minimal points or minimum points. Minimum points, it exists. It's unique. Otherwise, you have lots of minimal points. Where are minimal points for this case? This is a K comparison rule defined by a probable. Suppose here, probable is R plus two-dimensional space. And because this probable is self-dual, so its dual point is the same as itself. How do we find, because in this case, no minimum points, right? But there are many minimal points. Minimal points where? If you remember, how to find how do we, minimum points means this set. Suppose this is the minimum points. Then these sets, if these points minus K, you should consider here is a set. It's a set, 1 point set, minus K, which is in this yellow region. This yellow region, this yellow region. Then there's a separating hyperplane with normal vector line passing these points that separates the set O and this set. Okay? Then this point is a minimal points. It's the minimal points. Okay, this is what we have covered in chapter 2 about this. So, meanwhile, this is equation 4.125. This is also the problem. We have introduced in chapter 2, right? Which is given by this. How do you find these points? Y is the whole set O. We want to find the minimum lambda transpose Y. Lambda transpose Y. So that means this is separating hyperplane. You shift this separating hyperplane along the direction lambda. Then you move the line that represents the maximum increasing direction of lambda transpose Y, right? So you're going to find maximum supposed to be here, but minimum happen to be here. That's what we want. So this is also equation 4.125. So then here, okay, last time, we say the middle point is argument minimum, right? This is a remark. And then you test the order y greater than equal to 0. This is a proper cone, dual cone, because the illustration is for k equal to first orphan cone, which is a self-dual, so k equal to k star. So this is the way we can, given a lambda, we can find the minimal point. This is equation. This is the equation we base on, which is come from remark 227. Then you can check. I can show you 227. So page 108. 108. Page 108. Okay, then this is the minimal points. Minimal points. We have this equation. This is the O, corresponding O. Lambda is belongs to K star slash minus origin. This is a minimal points. This is a minimal point. When S is convex, when S is convex, then you can find the minimal points. Okay, then maybe you can, when S is a convex set, so remember there is a figure, page 90, in chapter 2. This is a S, now it's O. Then this is the minimal points minus K is here. So there's a separating hyperplane with lambda in K star minus origin, right? And if this axis is one of the minimal points. Okay, there are many minimal points over here. Suppose S is convex, then all the arc here are minimal points. Okay. Okay, that's back to 108. 8. 108. So this is what we, with this remark, we have after some analysis, we end up with this equation. This equation by separating hyperplane theorem. Then now we should be back to page 206. I'm sorry. You don't talk. Thank you. 206. 206. Okay, this is the equation, corresponding equation. Okay, lambda is here. Okay, that's the reason why we have used the equation for 0.125. So now for these the set. So how do you find all the minimal points? And can you tell these minimal points where they are? They are from B to C, from D to F, right? From D to F. This is not, not, they are not minimal points, because you can, if you shift this set, if you shift this set, to here, then this point will be smaller than D. So this pink color are not minimal points. And also this part, you are not able to obtain them. You don't need to obtain them. They are not minimal points. But here are, yes, minimal points. They are minimal points. Okay, then how do you find them? By using 4.125. Because the lambda is in K star not equal to 0, then if you do this, you can find out from B to C, from E to F. Because the lambda is greater than equal to 0, that means this direction, or this direction, or this direction. Then you can recover B to C and the E to F. However, you also get something wrong. From A to B, see the for lambda 1, there's minimum points happen to be had on this boundary. But from A to B, they are not. Only B, only B. Okay, then those solution. So those solution in green color here, we will obtain the set we call S plus on this boundary. But as you know, this green color here from B to C, E to F, they are minimal points, but they are a subset of S plus. Right? When you choose lambda greater than equal to strictly greater than 0, that means lambda 1 is and the lambda 2 are excluded. Then you're going to get from B to C and E to F. But F is not, you will not get it because this direction, this lambda 3 is not included for F. So you won't get it. In other words, B is non-smooth. You will get it from lambda 2 between strictly greater than 0. But here you don't. Here you don't, because you never get a chance to make your lambda to be lambda 3. Okay. So this set containing all the points from B to C and then E to F, not including F. So they are partial here from B to C, from E to F. But you never touch for E to E because this O is not convex. If O is convex, you indeed you can recover them, you can find them. But because it's non-convex set for O. Okay. So that's why. How do we find them? For now, convex vector optimization. Suppose F0x is K convex. K convex. We have defined K convex. We also have some examination problem regarding K convex. K convex. So the problem is convex. And the illustration here, I didn't say the function F0 is convex or not. Even F0 C is convex. O may not be a convex set. It's still possible. However, F0 is K convex, a feasible set. An ordinary feasible set is a convex set. then the corresponding O still may not be convex. The O. But the set O plus K, you draw it, then you will find it's like this is a non-convex, but this O plus K is here. You can practice the proof. This is a convex set. If it is a convex set, the minimal points happen to be here. The same as O. So, for convex problem, even O is not convex, but over here they are smooth and convex. But here is not convex. But we're not interested in that portion. This is a called parental boundary. So this is a term. This is a term. Plus plus is a subset of P. And the P is a subset S plus S, because you never miss anything on the constellation here. You never miss anything here. And you don't have mistakes. So you can so those you guarantee. You get a S plus plus is a subset of P. This is a whole P, subset of P. And P is a subset S, S plus. Okay, that's the main idea. The detail, I like to leave it to you. I don't want to repeat everything in detail, then the time is not long. Now we're starting from here. Now, that's the example. Suppose we want to solve this problem. The objective function is matrix, subject to these constraints. Here is also generalizing inequality. This is I didn't mention capital K proper point. That means it's a PSD point. So let's see how do we solve this problem. We check, as you know, the extreme points. If they exist, there are multiple extreme points. So that's considered to do this, to solve this problem. Lambda transpose Y. This is for vector case. For matrix case, given a W, because a PSD point is self-dual, so W is any matrix in PSD point. Then this is the inner product, right? The inner product like is a matrix inner product trace. So given a W, then we can find a minimal points. Find the minimal points. Okay, then let's give an example. So this is two substances. Two instances. You can choose one. The first point, point solve is 4.133 by setting W1 identity matrix. W2 is also a PSD matrix. You should be able to justify it as PSD matrix. Diagonal term must be positive. Its determinant must be positive. Okay, then suppose AI will constraint, the inequality constraint AI here. These three. These three. And the A1, A2, A3 are also PD matrix. This is the output that we choose to make them PD matrix. Okay, what is the minimum point we can find for W1 and W2? We just solve this problem. Okay, just solve this problem. Okay, then because of the solution, can you use directional derivative criteria, which is introduced earlier in this chapter, right? Usually it's hard, but the KTD condition can help you solve it much easier. You can also use convex solvers or CVX to give you a local solution. Then the last, there's an appendix introducing the current the state of off-the-shelf convex solvers available and free for you to use to test to see if you can find a solution. You get one solution, X, W1, you get a solution, let's say capital X1. Then it must contain A1, A2, and A3, right? So if you remember, because A1, A2, A3 are PD, so X must be a PD matrix. And meanwhile, each PD matrix defines a ellipsoid. Okay? Ellipsoid. So we give an illustration of the result. For W1, we solve minimum point X1. They contain X1 form a ellipsoid that contain A1, A2, and A3. This is the only way. To illustrate the results. This is not a vector case, it's a matrix case, and this is the only way I know how to illustrate. Another minimal point is X2. We choose W2 in solving the problem above, and you get X2. X2 is this one. This one. It also contains A1, A2, A3. This result it was by my former PhD student. He's very, very smart. He's the author of this paper award. Okay, this is the concept with the illustration for that matrix case. So because we have introduced in chapter 2 how to illustrate when you compare two matrices. That's minimization. What about maximization? If you have a convex problem, F0 is a K convex. Fi is convex. Hi is also convex. So the same thing happens. So you can only find maximal points. Maximum point does not exist. And that's most of the situation in engineering. Okay, then F0 now is K contained. Is a vector or matrix. that means minus F0 is K convex, right? Because C and the feasible size is convex. Again, through the above, you say to find a maximal point. Again, line the transpose F0 not greater than 2 equal to 0. Not equal to 0. Given a line, we get that a Pareto boundary F0 y, we get a 1, or we get an F0x. Okay, this approach, sometimes we say this is a scalarization of 4.418. 4.418 is a definition of the Convex optimization. Okay. So how we find maximum points? We say it's Pareto optimization. In many cases, we are not only interested in X, we're more interested in F0X. That's the boundary points. This is another example to illustrate what I said. This is a multi-channel communication, or there are many subchannels. For example, in OFDM system, so find the communication modulation technique. You divide your transmission back into many small bands, which then you have a subchannel allocated to the different users. So we would like to maximize throughput rate. The throughput rate when user 1 is we use the channel 1 transmit the power P1, but this channel from transmitter to receiver, the channel quality for here is a simple example for illustrating the idea. We suppose the receiver of has only AWGN, then no interference. This is a simplified case. But when you simultaneously transmit your signal, interference will happen, and that's it. But this is only for, you can consider this as like a 20 example. So only AWGN, no difference between subchannels. In user 1, this is the throughput rate by Shannon capacity theory. So it's a log 2, 1 plus P1 over sigma 1. And it's a bit per second. Then this is a user n. First of all, let me ask you, this objective function is a vector, right? Is a vector. Is that K convex? Look at this. R1, this function of P1, the variable is P1 is the power for subchannel 1. Is this function a convex function of P1? It's a concave function. Log is a concave function. 1 plus P1 times over sigma 1 squared is a fine function. So their composition is concave. Right? Convex function composition would be a fine function, still convex. But concave function also is still concave. So this is concave, so this is element-wise or component-wise concave. So this is R plus concave. So this problem the constraint. This is linear constraint inequality. So linear inequality. P1 represents power for user 1 or subchannel 1. P1. Okay, so this is a convex constraint, right? Linear inequality is convex. So this is a convex problem. However, how do you find the maximal points? Again, you need to choose a lambda. Lambda greater than equal to 0. Or equal to 0, right? Then, so some explanation. You just choose lambda greater than equal to 0. Then we try to find out the set of Pareto boundary. That means you solve this maximization problem. And to end up with these, this is like a y. So sorry, this R. This is a true Pareto boundary. Let me see. That's right. This. I don't know why I should write it Fy. Yeah, this is scalarized. I define this. This is F. Here. Yeah. Here's R. This is an objective function. This is scalarized. This is different from what I mentioned, F0. So we want to find these. We want to find this. Okay, then you solve the above problem, you will end up with this is a numerical example. Suppose we have only 2 subchannels, Y2 subchannels. This is the easiest way to illustrate the concept. For 3-dimensional, for 3 user case, then for 3 subchannel case, it's very hard to show the numerical results. So this is R1, this is R2. The vector R is only 2 components. The O, when you are given the channel condition, for example, sigma 1 squared and sigma 2 squared equal to 1, then this is O. You will get O here. You get O. Then you choose a line. What is the line? You choose lambda 1. So half of lambda 2, you get this. Lambda 1% of lambda 2, you get these points. So you get lambda 1 is 2 times lambda 2, you get these points. Look at this. This is a typical example. Then this is they are Pareto boundary points. Pareto boundary points. Then they when you choose a line, that you get a set of lambda 1, lambda 2. This is like an objective function, for each subchannel you want to maximize. But lambda I represent because they are non-negative, like weights of 比重. The larger the weights, the more the solution. So the rates turns out is lambda 1, R1 is the lambda 2, R2 summation. The larger the weight, the larger the results. In other words, like you pay money. You pay money for your service. You can get a service. The throughput rate. If you pay your example, circle, subchannel 1, paid by user 1, it's 2 times. Then channel 1 transmission rate will be more than 6 here, beats per second per hertz. But for user 2 only get 5. 5 point something, this is 6 point something. So like this. 那就好像是钱付的多的，你的throughput rate就可以比较大。But this is when you pay the 2 sub-channel, paid by users the same weight, then you get the same. This is the same. This is 6 point something. This is also 6.4. No, 6. 它是 below 6. 从这边看，就是它刚好是对称点，5点几，它刚好是对称点，是对称点。只是因为这个 scale， 这个 scale 是0到10，这个 scale 是0到7，看起来好像不对称点。There's symmetry. For this case, if the channel condition is different, more noise. Channel 1 is more noise. So the distribution for rates, for the 3 corresponding lambda 1 and 2 will be different. So you get a new O's here. For those 3 lambdas, then you can get corresponding solution. Okay? I'd like to mention this. For this maximization, is O convex set? The answer is yes. Obviously, it's a convex set, right? Then this O is also convex set. Right? That can be shown. 这是可以证明的。This is a convex set. This is always a convex set. Maybe you can see that this is a numerical example, but theoretically it can be shown. The analysis is very important to PhD student. Then, as you know, many intriguing properties. Sometimes it's hard to clearly or analytically or numerically or to support or to explore. If you have you can theoretically prove it, then that's the job is done. So my former PhD student, he's very good in analysis, in linear algebra, random processes, and optimization. He surprised me lots. So that's the reason why he will get best paper award. But the detail of how to prove R1, this O is a convex. There's some story. I think I don't have time to show these. This is given by remark 4.12. You should go through and read. How do you prove? Otherwise, you just use what you have learned so far, and you should be able to prove. Okay. This is section 4.4. Now, we move on to section 4.5, quasi-convex optimization. What is a quasi-convex optimization problem? It's nothing but a different optimization problem. The convex problem, F0 is convex function. Quasi-convex problem is F0 is quasi-convex function. That's it. The feasible set remain the same. Convex set. So, F0 is quasi-convex. Okay, then it is you know it's a quasi-convex, but not convex yet. Are there any optimality criteria for you to find the optimal solution? Like convex gradient fx star transpose x minus x star greater than equal to 0. 方向导数大于0。Answer is too bad. We don't have an optimality condition. We don't have the optimality criterion, which is if and only if condition. It's the only sufficient condition. This is a remark 4.2. What does it tell? The sufficient conditions given by 148. So this is very close to the first optimality condition. For convex problem, here is greater than equal to, right? So, but here is only greater than 0, which we claim. And you can get an optimal solution for quasi-convex problem. If it is a convex problem, then it's if and only. But now, for quasi-convex, here is strictly greater than 0. So if your optimization criteria, optimality criteria is only sufficient condition, is hard to use, then if you apply it, if you can find it, oh, that's fine. If this sufficient condition does not hold, you still can find the optimal solution, but you don't know. So this criteria is, to me, I think is not very useful. But theoretically, you can prove this is a sufficient condition. The proof is also very easy. One line is the proof. Because, the statement is only by contra positive statement. Contra positive statement. See, because F0 is a quasi-convex, by the first order condition of quasi-convex function, this is it. F0y plus the F0x implies this in chapter 3. However, we are given the conditions here. This is strictly greater than 0. So that means this is not true, right? If it is this is true, this is optimal, the solution X is optimal. But this is not true. So this is not true. This must not be true. Right? This must not be true. That means Y is not an optimal solution. Sorry, X is an optimal. Right? This is not true. Then this is not true means F0, and that means F0x strictly less than f01. That's right. This is a if this is not true, if this is not true, then this is not true, then this is not true. This is not true means f0x strictly less than f01. Right? So this is the optimal solution. This is for all y in C, y not E. So this is the optimal solution. So this theory is based on the contra-positive statement of this quasi-convex function, definition of quasi-convex function. So this is not true. This is true. This is true. Then this is true. This is true. This is true. And this is true. And this is not true. This is not true. This is not true. This is true. So the proof is only one line. One line. However, as I say, sufficient conditions are hard to use. But are there any practical approach for finding for solving quasi-convex function problem, or quasi-convex problem? The answer is unfortunately yes. This is very popularly used in engineering or in communications. So let's look at this quasi-convex problem. That's the first. We reformulate. You have learned some reformulation, AP graph representation, linear equality elimination, function transformation, and change of variables. Let's use a quasi AP graph representation. Minimize t, epsilon. This is nothing but the AP graph representation. This is the original constraint. Now we have a new variable t, and we have a new inequality constraint, f0 less than equal to t. Look at this. The feasible set convex for this problem. For this in the problem 1.49. Objective function is 1 variable t. T is a linear function on its own. So objective function is convex because it's affine. Fix less than equal to 0 is convex constraint set. And Ax equal to B, yes, convex constraint set. What about this? F0 less than equal to T. Because F0x is quasi-convex, less than equal to T, this is sub-level set. If you fix T, okay? If you fix T, this is convex. Fix T, T 固定的话，它是一个 sub-level set, so it's convex. Right? So you only can fix T. Otherwise, the feasible set is not convex set. So, with this observation, CT here. CT is already here, here, in here. F0x less than T. And this is a feasible set for a given T. Feasible set given T. If you increase, if T is less than S, then you replace this by S, then you get a new say CS is a CT. So it's a subset of CS because this is the largest subset. Okay? However, when you give anytime you give a T, the feasible set is convex. So in other next I'm going to introduce the bisection method. This is bisection method to find a numerical solution. Okay, let me tell you what. The algorithm is demonstration is easier to follow, to understand the concept. Suppose your CT is here, center. Your T is here. And this bisection means you choose a lower bound, is the upper bound of the objective function. Then you will say, upper bound, lower bound is easy to, or is hard to determine. In engineering, usually is high. For example, power minus 0, a maximum transmitter, the power, for example, 10 watts and 100 watts, it's never 1,000 or 10,000. It depends on when you design your system. You know maximum you need to, you can handle the maximum power. That's not too hard to determine. Upper bound, lower bound. Okay, then look at this. U, CU represent the feasible sets here, right? So we want to make T, this is optimal value, right? P star is optimal value. This is optimal value is here. When you lower U here, what do you have? Then you convert your feasible set from CU to CT, smaller. But if you set your lower bound for these L, or is the feasible set? Because L is lower than P star, it's impossible. Right? You don't have no solution. Suppose P star is the optimal, right? If you choose optimal F0x to be L, it's a sub-level set, is empty set. So if you test the average of L plus U divided by 2, then you can make, for this case, you can find a point in here. Right? If CT is not empty, you can find one. What is this problem? This is a feasibility problem. As long as you, is a feasibility problem. Is a convex feasibility problem. Convex feasibility problem. Convex feasibility problem. That means you make f equal to x equal to 0. Or this is a nice constraint function. Yourself, when you can define f0 x equal to 0. Feasibility problem. Okay, that means you can you run CVX or wherever you can get the solution over here, which is within CT. That means, what does it mean? That means any solution is accurate to this degree from the objective value turns out larger than P star by some amount. Okay? But next, we want to shorten CT again. Then this is a new U. That's a new U. Then you lower this level to this level. Then average between L and the new U. The average is around here. Then we test the feasibility problem. You find it, say M%, right? M%, then that means L is too small. You're going to move up here. Then next step, the average of this level and the U P here. So here. Then you can find some solution with a smaller interval, which is closer to P star. Right? This is the way. So you just change U with L and U and L. Finally, you can, when U and L, the distance is lower than a certain parameter, we say tolerance, absolute. We say it converges. The solution, we say is the absolute optimal. If you get a, so this is the algorithm. This will say it's not MBD, lower the upper bound, otherwise you move the lower bound up to T until U minus L is within absolute. That means your solution, you set this parameter after convergence, you can claim the solution wherever it's within this accuracy. We say this is an absolute suboptimal. This is the terminology. Absolute well, anyway, so you just be within P star plus absolute, then you stop. So your solution is an accurate, we say absolute suboptimal after convergence. This is also converge. This is a convergence criteria. When your algorithm stops, then your solution will be P star plus epsilon within this limit. Okay? So that's the idea. So I think it's a very straightforward thing. Let's give you some examples. First of all, we define the examples at F0 given by this. What is this? This is a denominator is a linear affine function. Numerator is also a affine function. Right? This is a variable. This is a variable. This is a variable. Is it? If this is a objective function of your problem, is it Convex problem? Is it Convex function? It is a quantum-Convex function. In chapter 2, we have introduced this. This is called linear fraction, function that preserve the mapping from a Convex set to its image Convex set, if you remember. Okay, let's consider this problem. It's a linear fractional problem. Of course, the denominator must be positive, otherwise it is not defined. So this is the problem that we solve. The denominator must be greater than 0. Then ax less than equal to b. Is this problem convex? The answer is definitely not, because M0 is quasi-convex. But the feasible set is convex, right? Linear inequality is also linear inequality. So the constraint set is a polyhedron domain. So don't expect to use optimality condition or directional derivative non-negative. It's not applicable. So how do we reformulate this problem? Again, look at this. By epigraph reformulation. The objective function comes here. Then through some function transformation, delta something should be simplified. You end up with this is the you end up with this. This is still quasi-convex problem, and this integral form is not convex. If you fix t, then this is an ordinary inequality, right? Linear inequality. It's an ordinary linear inequality. Okay, so we end up with this problem. This is it, and then we can apply by fixed t. Apply bisexual method to get a numerical solution. Okay. Just applying that above algorithm. We say that's a bisexual. And it's a to the numerical solution. It's very fast because the binary is fast. It's a lot. Okay. What about if your objective function is a maximum set of you just think this Ci transpose x plus Ti divided by Fi transpose x plus Ti. This is a linear fractional function which is quasi-convex, right? The pairwise maximum of quasi-convex is also quasi-convex. Did we have an examination problem? According to difference. So this is a quasi-convex function. Of course, all the numerator must be positive. And then ax less than equal to b is nothing but a linear inequality, a set of linear inequality. So you can apply bisexual method to problem 157. So we say quasi-convex function bisexual method is very useful in solving the quasi-convex problem. Okay, let's come back. Let's come back to see this. I am asking you Formula 153, although it's quasi-convex, but you never. This is the only way. I will say that of course you can get a numerical solution for 53. On any other approach to solve this problem optimally, the answer is yes. Because you have learned some problem reformulation we introduced earlier in this chapter. Reformulation approach, epigraph representation, the linear equality elimination, function transformation, change of variables, etc. or the combination of them, right? Why don't you move forward to reformulate these problems? Reformulate this problem into a common problem. Sometimes this is doable. When quasi-convex problem, definitely numerical solution I can get within some accuracy. If you can move forward, reformulate the problem again, make it complex, then you can get an optimal solution one time. Okay, how do we do this? Nothing but change your verbals. We're going to make this verbal change. This is verbal change. This is from here. 4.1.53. You make some verbal change. You get new variable z and y. Then reformulate the problem into a linear problem. Then you can have an optimal solution. This new variable is 1 and z. This is a linear inequality, linear equality, linear equality. So this is a linear problem. You can have an optimal solution. To get optimal solution, put it back here. You get optimal z, and when you want to, actually, the solution of x is y divided by z. So you can come back. Okay. There are some details about the, I leave it to you. I leave it to you. We still have I want to stop today around in 10 minutes, and so that we can return the examination sheet to you, so that you can check if all the grading fair to you. Okay, this example is very, very interesting. Earlier in this chapter, we have an example, which is, we say, optimal power assignment. What is that problem? So we need to go to page 196. 196. If you remember, this is a scenario. Each transmitter wants to transmit signal to its associated user. Then you're going to have a large interference. Then each receiver, the signal received, the quality, we use this measure, this matrix. The signal to interference cross-noise ratio is our signal power in the numerator. This is interference. This is AWGM. So this is power assignment. How do you allocate the total power to minimize the total power of the system? Okay? This is summation of P1. You have the pairs. You want to the SINR gamma I greater than some certain threshold. This quality of service guarantee. Then, if you remember, for this problem, through some simulation, we come up with a linear program through function transformation. So this is what we have we have learned before, a week ago at least. So now we come back to this problem again. Let's look at page 216. 216. Let's look. In other words, different problems, different way to solve. But now we reconsider this problem into another problem. In other words, we are not minimizing, we are not going to minimize the total transmission power. We want to maximize the worst case. Worst case, we want to maximize. We want to maximize the minimum power of the K user. We want to minimize, we want to maximize the minimum power. Sorry, it's not power. Gamma is a QoS, quality of service, 就是 SLA 收讯品质要最差的收讯品质要好 maximize。This is worst case. Under the constraint, power small pi must be less than or equal to capital Pi, because the power is always limited. So this is the problem we want to solve. Rather than minimize the total transmission power under constraint QRS gamma I greater than or equal to 0. This is another type of problem in engineering communications. Okay, the first step, you're going to solve this problem. It's match-made. It's not a standard form minimization problem. You can apply this equivalent transformation. And 4.11 and 4.12. And this problem turns out to be given by this maximum. This maximum turns out to be max mean, like this. Okay, this is sorry, this is not reformulation yet. This is the definition. We just apply the definition. Just apply the definition. 这是现在这个只有用到定义。Next step is reformulation. We convert this max min into minimax. The objective function now is 1 over gamma star. So minimum, max, 1 over gamma I. This is given to us 4.11 and 4.12. Now you can practice after the lecture, and you can prove yourself. But now your objective function is a maximum I for K, 1 over gamma I. Then we have minimum and maximum I. 1 over gamma I is 1 over this. So inverse of this thing. So this is the problem we will solve. Look at this. Is that convex? This is objective function. This is objective function. Is it convex? It's exactly this form. Right? Exactly this form. This maximize, this is a linear fractional function. Component-wise, maximum. Point-wise maximum of quasi-convex function. So this is a quasi-convex. It's a quasi-convex. This is feasible set 是1，就是小 pi 小于等于大 pi， maximum power 是 linear inequality it's very complex. So this is a quite complex problem. Then you can apply bisection method to get numerical solution for your p. So you get a solution. This p solution is the same as 1/9 solution. But this optimal value is gamma star. This optimal value is 1/gamma star. That's alright. That's true. As long as you get optimal solution with pi, job is done. Is that clear? In class, then because the time is very limited, then so that I checked the calendar. Our final examination week is January 11th through 15th. So yes, it does. I'm looking at this. I have only 1 month to finish all the material because next week we can finish this chapter definitely. But chapter 9 is essential. It's a 非常非常重要的一个 chapter, and then it is a little bit long, and concept is a little bit hard to absorb, to understand. Then chapter 9 requires you understand chapter 1, 2, 3, 4. Then you can learn very easily. This is a causal system. So try your best to learn. And then from now on, you have more chance to see how practical, how we apply this theory in engineering problem communications. They all presented in chapter 5, 6, 7, and 8. But during the semester, I may not have time to present too much about the applications. But when you read chapter, for example, 8, I already tell you, provide you with those where I use. In chapter 3, where I use this, where I use this. Now we formulate this problem. Now we solve this, and this problem. In the future, if you get a chance to be the pioneer, 你要当先驱，你第一次破解这样的问题。Usually, you get attention from the international research community. Well, then your paper get a high citation paper. Then you easily get recognized. Then your foundation must be very solid. When you define a problem, usually they take the first look. The problem is that that's not homework. Research is not homework. But research result published can be used as a homework. But when new problem, it's not, usually it's not homework problem, because you don't know the solution. You need new theory, you need new analysis, you need a new experimental result to verify. It is rigorous, it is justifiable, and it is clear, concise, and complete. That's what you need to do. Then where to use the fundamental principle theory, like 黄飞鸿，你就很快就把它处解，那你就很厉害。When your work is pioneer. Okay, so come back. Good. When your work is a pioneer, you have no one to compare. usually you publish your work. What is the currently state of art algorithm? Usually you need to compare what existing, what you go beyond the current algorithm and current knowledge. So what are your contributions? Contribution, not if it is only tuning parameters, that's not contribution. Forget it. You want to make contribution when you are the pioneer to solve this problem. You have no one to compare. So that's fine. You don't need to compare. You say, you can create this on in your research work as a client. So far as we know, this is no previous contribution, no previous work to compare. That's fine. You're the first one. If this area, there are quite some state-of-art approaches, then you need to claim your contribution is novel, and you have to compare with this. How much is your contribution? If it is trivial, marginal improvement, then good journal won't accept it. Contribution is trivial, it's not below a threshold. It's how long we hear. Research, not because your research work, you cannot say, mine is not the same as the other one, so this is a contribution. The answer is no. You have to claim how big the contribution. That's the research. You tuning this, tuning that, that's useless. Don't waste time. So you need to have a novelty, innovation. That's useful. So sometimes you can have a research work, high citation by several hundred, sometimes zero. So you publish, but no one cares. So for PhD,